Hello, in this video I will discuss SPADE, which stands for Sparsity-Guided Debugging for Deep Neural Networks. In summary, SPADE utilizes pruning techniques to enhance various interpretability methods such as neural visualization and saliency maps. But why is interpretability important? It helps us understand how neural networks make decisions. This is useful for debugging, for building trust, it is required for some regulations, and is helpful for model comparison. For example, when you want to debug your network, you are more efficient if you know why the network made a decision. Or it is required for some regulations you showed how the network works. This is because some networks have been shown to have like racial or sexual biases, and ensuring that your network doesn't have these biases is important in many cases. And it can build trust. For instance, if a surgeon wants to start an operation based on a model's output, it needs to be double check the model reasoning. And for model comparison, in many cases you want to compare your model not solely based on their accuracy and like check if the model is based its decision on spurious correlations. So how does a SPADE work? It starts with a dense network and an image, and then it prunes this network using this image and removes unrelated weights to this specific image, and then interpret the pruned network on this image. More specifically, SPADE first generates many similar images to this image using image augmentation, and then it prunes the network using these images, and then it applies interpretability method to the input trace, which is the pruned network, and this image, and get the outputs of the interpretability method. So how SPADE prunes a network? In the pruning phase, SPADE first computes the input and output of each weight matrix, and then tries to find a sparse weight matrix that behaves similarly to the dense weight matrix. And what do I mean by sparse weight matrix? I mean a weight matrix that has many zeros in it. And by behaving similar, I mean we try to minimize the norm 2 difference between the original weight matrix output and the sparse weight matrix output. So now that we know how SPADE works, let's discuss a SPADE for saliency maps. Saliency maps are interpretability methods that say which part of the image is important for a model prediction. And as you can see in this image, SPADEs help model to came up with a cleaner saliency map compared to the scenario when we don't use a SPADE. To evaluate saliency maps, we use a technique called backdooring. In the backdooring, we plan to backdoor in the model such that it associated some emojis with some classes. For instance, in this case, the model associated heart emoji with goose class, regardless of the background. In this way, we have ground truth for our saliency maps. This is because, for example, when the model classifies this image without the heart emoji as fox, and then we add the heart emoji, and then model predicted goose, we are somewhat sure that the reason behind this change of prediction is the heart emoji. So we use this technique to evaluate our saliency maps and measure how much of the saliency map focus is on the heart emoji pixels. As you can see, SPADE improves all saliency map methods in this benchmark, including input X gradient, deep lift, LRP, guided backprop, lime, and many more. We also evaluated SPADE using other benchmarks like insertion and deletion, and SPADE improves most saliency maps in these benchmarks as well. We also provide some samples to let readers qualitatively evaluate some SPADE saliency maps. And as you can see, in many of these samples, SPADE's saliency maps are more focused in the right object. Okay, let's discuss neural visualization. Neural visualization is a method that generates an image that highly stimulates a specific neuron in the hope that this generated image will help us understand that neuron better and understand what concepts activates that neuron. However, these visualizations aren't informative enough many times. For example, assume that you have a network that misclassifies these two images as lighter, and you want to know why this misclassification happens. So you can apply neural visualization to the lighter class, and you will get this image, which is not helpful for your need. However, if you first apply SPADE and prune the network using this image and then apply neural visualization, you will get this neural visualization, which is helpful and suggests that the reason behind this misclassification is the match-stick heads. It's the same thing for this spotlight image, which is misclassified as lighter. If you first prune the network using this image and segmentations, and then apply neural visualization techniques, you will get this neural visualization, which suggests that the reason is the light in the spotlight image. So how we evaluate the SPADE under these neural visualization settings? We conducted a survey that asks user which region of the image best matches a neural visualization. If the user guessed correctly, then we assume that the neural visualization provided enough information to the user that the user is able to guess which part of the image is most relevant to that neuron. More specifically, here I showed 3 examples that a user might see during this survey, and here is the second example, and this is the third example. And in the third example, we showed neural visualization of the fence class and an image, and obviously the most related part to the fence class is this region rather than this region. And if the user guessed correctly, we somehow know that this neural visualization is informative enough that the user is able to understand that this region is more relevant. And as you can see in the survey results, when we get the neural visualization from the SPADE, users are less undecided, and when they decide and choose one option, they are more correct. So we can assume that applying a SPADE before neural visualization is improving the visualization's helpfulness. We also applied a SPADE to the backdoor model I discussed earlier. Without a SPADE, you cannot see that any trace of the related emoji in the goose class, for example, which, as we know, has a side functionality of detecting heart emoji. You cannot see any trace of heart emoji in this feature visualization. It's the same case with orangutan class, which has a side functionality of detecting a star emoji, and you cannot see any star-like pattern in the neural visualization of orangutan class. However, if you apply SPADE, which means that you prune the network using an image which contains heart emoji and then apply neural visualization, what you get is clearly showing some heart emojis. It's the same case with the star emoji and orangutan class. If you first prune the network using this image and then apply neural visualization, in the resulted neural visualization, you can clearly see some star-like patterns. And if you prune using a normal image, you will still get like helpful neural visualizations, which in this case, for example, suggests that the fur or neck or head of the goose is important in detecting goose in this image. But how SPADEs work? We believe that SPADEs works because neurons get activated by different concepts, which called polysemanticity, and since they get activated by many concepts, it's harder for the interpretability method to interpret the network. When we apply SPADE, normals become monosemantic and only becoming focused on the functionality necessary for the input image. We show this in a toy example. We trained a network that classifies between blue dots and orange dots, and when we apply neural visualization, the only thing we get is the visualization from the bigger circle, completely missing the smaller circle. So this network is clearly a polysemantic network because it works on two different areas. However, when we apply a SPADE and prune the network using a sample from the smaller circle, all of the feature visualizations are from the smaller circle, which shows that the network is getting focused on the smaller circle. Okay, so let's talk about different SPADE variations. Variations are coming from the pruning method we were using. We were used two different methods, mainly optimal brain compression, and this is a bit slower method which took like 16 minutes per sample. But we also applied like faster pruning methods like a Sparsity-GPT, and Sparsity-GPT, it takes like 23 seconds per sample, and if you have a batch of samples, you can parallelize them and the average time drops to 3 seconds per sample, which is a lot faster than normal SPADE, and it's also faster than many interpretability methods you want to use later. And the last thing I want to talk about is tuning the sparsity ratios. Like both pruning methods I discussed in the previous slide requires specific sparsity ratios per weight so that they are able to prune till that threshold. So how we tune these sparsity thresholds? What we did was that we started from the end of the network, like the classification head, and moved backward and tuned sparsity ratios of each layer separately, one by one, using an evaluation set. So since this process is time consuming, we also did a bunch of studies. Like we showed that linear ratios also work, like 0% sparsity for the first layer and 99% sparsity for the classification head, and interpolate everything in between. This also works. We also showed that few samples are enough for the evaluation set. We also showed that the sparsity ratios transfers from fastest SPADE to SPADE, so you can tune your sparsity ratios using fastest SPADE and then transfer them to SPADE and use a SPADE for the real task. And most importantly, we show that sparsity ratios transfer between datasets. So for instance, we tune the sparsity ratios for ResNet50, MobileNet, ConsNext, and if you want to if you have a ResNet, for example, ResNet50 network that trained on a different dataset, you can still use our sparsity ratios, which completely removes the sparsity tuning phase. And we also did a bunch of other studies, like we investigated which augmentations work. We investigated how SPADE work on other models like MobileNet, ConsNext, and BERT. And we also investigated what happens if you prune using another sample and then interpret the network on another sample. Thank you for watching.